All right, continuing on with section 1.8, we are going to discuss existence proofs in a little more detail. So I'm talking about proofs where you want to prove the existence of something, like the existence of an element in a given domain that satisfies some conditions. So the format would be like prove there exists X such that P of X. All right. Well, there's two main sort of the different methods of proving existence can be divided into two like groups. There's constructive proofs, and a constructive proof is essentially where you exhibit a element of the domain, a constant element, so we'll represent that by the letter C, for which P of C is true, right? So essentially, we're proving the existence by showing one. We're like, here it is, we're pointing to it and demonstrating that it works. And then we're deducing there exists X P of X by the existential generalization, which is one of those rules of inference. Essentially saying, hey, if it's true for one, then you can generalize it to this quantified statement that, is quantified existentially. So that's a constructive proof. Those are pretty straightforward. Then you have non-constructive proofs, which is anything else. Any other way to prove the existence that doesn't involve just pointing at and kind of like displaying a particular instance when it works. So an example of a non-constructive proof would be a proof by contradiction. Suppose you assume the negation of this statement that that for all x, not P of x. If you assume that and then deduce a contradiction, well, that would prove this. But you would have done it without ever actually identifying an element for which it works, right? For which P of C is true. That's non-constructive. So I'm going to show you an example of an existence proof. And the one we're going to go over is, the proof I'm going to show you for this is a non-constructive proof. This statement we're going to prove here, it's actually quite easy to prove constructively, and so I'm going to leave it to you to see if you can come up with a constructive proof for this statement. Here's the statement. There exist irrational real numbers, which if it's the term irrational generally only applies to real numbers anyway. So there exist irrational numbers x and y, such that x to the power y is rational, not irrational. So x and y are both irrational, but when you take one raised to the power of the other, you get a rational number. Okay, so reminder, for all real numbers, this was meant to be a real numbers set here. For all x in the set of real numbers, x is either rational or it's not, which would be irrational. The symbol, I've used the symbol Z for integers, the symbol R is for real numbers, the symbol Q is for rational numbers. But there's no symbol for irrational numbers. It's just real numbers that are not rational. So, what I've said here is x is not an element of the rational numbers to mean it's irrational. And this is technically an XOR statement. A real number is either rational or it's irrational. It can't be both. And then the definition is that x is rational if it can be written as a fraction a over b for some integers a and b. Okay, so the fractions are the rational numbers and the irrational numbers are everything else. So rational numbers, just for example, include things like 0 and 5 and -2, as well as 2/3 and 7/5 and -21 37ths, and so on. The irrational numbers are harder to get your hands on, but they include things like pi and e, phi, square root of 2, square root of 5, 2 plus the square root of 5. If you add an irrational number and a rational number, the result is irrational. That sort of thing. Oh, also things like the natural log of 2 is an irrational number. Yeah. So we're going to prove this. I'm going to do the proof on the next page. All right, so we want to prove there exist irrational numbers that when you raise one to the power of the other, you get a rational number. All right, well, so for the proof, let's consider the following. The square root of 2 raised to the power the square root of 2. Okay, the square root of 2 and the square root of 2. The square root of 2 is an example of an irrational number. Okay, we're going to get to that. but it's real in particular. And when you take a real number raised to another real number, as long as you're not dealing with 0, which might be undefined, this is going to be another real number. This is another instance of a set being closed under an operation. As long as you're not talking about 0, or actually, yeah, as long as you're not talking about 0 to the power 0, this is an operation which is closed. The real numbers are closed under exponentiation. So this is a real number. That's all I meant to say there. Sorry, it took me a long time to explain why this was a real number, but it is. Okay, so therefore it's either rational or it's irrational. Got to be one or the other. So now what we're going to do is we're going to break this proof into cases. One strategy that it's often, useful when proving things is to break it into cases. We know this number is either rational or it's irrational, so let's look at both possibilities. So case 1, let's suppose that the square root of 2 to the power square root of 2 is rational. So is an element of the set of rational numbers. That means is an element of, and Q represents rational numbers. So suppose that's the case. Well, since the square root of 2 is irrational, and I'm taking that on, as a fact at the moment, proving that the square root of 2 is irrational is something that the Greeks did a very, very long time ago, and it's a very interesting proof. I recommend checking it out sometime, but we're just going to take it as a given. So since the square root of 2 is irrational, we can go ahead and let x equal the square root of 2. That would be a valid value we could use for x. And also y equal the square root of 2. There's nothing about the statement said that x and y have to be different. So x and y are both equal to the square root of 2. Well then, x to the power y would equal this number, square root of 2 to the power square root of 2, which we are currently assuming is rational. I have exhibited an example. In this case, under my current assumptions, I've come up with an example of a situation where an irrational power of an irrational number is a rational number. So therefore, there must exist x and there exists y, irrational such that x to the power y is this. All right, so I proved it in that case. But now let's look at case 2. So the case 2 would be, suppose that the square root of 2 to the power square root of 2 is not rational. Okay, now that's an irrational number. Well then, that's an irrational number, which means it's a valid option for x or y. What we're going to do now is say, let's let x equal that number. Square root of 2 to the power square root of 2. And we're going to let y equal the square root of 2, which we've already identified is an irrational number. So now x, given under our assumption this is irrational, we're going to have that be x, and y is going to be the square root of 2. Now, if we look at x to the power y, we have the square root of 2 to the power square root of 2, and then all of that to the power square root of 2. You may recall that a rule for exponents combined in this way here is that you multiply these powers together. And the square root of 2 times itself is 2. So this is the square root of 2 squared, which is 2, which is an integer, and is therefore a rational number. So it works. So again, I have exhibited, in this case, right, I've exhibited a pair of numbers which satisfy the claim. So therefore, in this situation, there exists x, there exists y, irrational numbers, such that x to the y is rational. Okay, well, in either case, I was able to find an example, right? And I don't know which of these two cases is in fact the real true case, but I do know that one of them has to be true, right? That number is either rational or it's irrational. So if I can prove it in either case, it must be true. So the claim is true in either case. So it's true, so it must be true overall. All right, and that's the proof. Let's QED that. So you might be thinking to yourself, wait a minute, Tristan, you said this was going to be non-constructive. It seems pretty constructive, right? Because in this situation, I actually said let x equal this. Let me go through with another color. Let x equal this and let y equal this. And then I was like, hey, check it out. It's, it's a rational number. And then in the next situation here, I said let x equal this and let y equal this. And then I said, hey, check it out. Again, it's a rational number. But why is this not constructive? Well, the reason is because at the end of the proof, can you tell me an example of two irrational numbers that when you take one raised to the power of the other, it's rational? Not really. I mean, unless you thought of a different one that I didn't mention yet. But I didn't prove that either of these two cases is the real case. I just proved that it must be one or the other. Right? So at the end of the proof, you don't actually have holding in your hand, you don't actually have an example, right? You just prove that an example must exist because in either of the two cases, you can find one, but we don't know which case we're in. So that's why this is technically a sort of a clever, non-constructive proof. Now, if you ask me, I think that I'm pretty sure the real situation is case 2. I'm pretty sure square root of 2 to the power square root of 2 is an irrational number. You can check me on that. But I challenge you now to think about this problem and come up with a constructive proof. This isn't like a super hard thing. I just think it's kind of fun to think about. And I think if you think about it and think back to algebra class, I'll bet you could come up with an actual example that you know works and that you know proves this constructively. There we go.